Bismillahirrahmanirrahim. This video is about power system analysis and design, a book by Glover and Sharma. And here we'll be discussing example 3.7. This is on the request of a student from Bangladesh. So before we go to the actual example, let's see some of the transformer rating parameters that I hope you already know. I'm just going to repeat. Let's say this is the question given or the transformer parameter given. Single phase 2-winding transformer is rated to 167 kVA. So this is the power. And these are the two sides of the transformer rated. That means power is 167 and 19.9 is on the primary side and 6.35 is on the secondary side. Now this is, since it is single phase, this voltage will be line to neutral. This is neutral, this is line. So 19.9 is voltage line to neutral of the primary side. And similarly, this one is line to neutral on the secondary side. So when single transformer is given, we have to follow this technique. The other option is that a three-phase transformer is rated at 500 kVA, and this is the voltage rating. Now, in the three-phase transformers, this is the total power. 500 kVA is the total power of the three transformers. And in this case, the voltage given is line-to-line voltage. This we have to be careful. This was line to neutral, but in this case, it is line to line, 34.5 and 11 kVA. Another option could be that the question says three transformers, each rated of this, form a bank. So it's the same like this, but these are three different transformers. Now, in this case, either we can use the single parameter of the transformer, or we can multiply by under root 3 to get the three-phase rating of the transformer like this. So this is another way of doing it. So multiplying by under root 3, we get 34.5 and 11 kVA, which are the V line-to-line primary and V line-to-line secondary. Okay, now I'm sure you know the transformers can be connected Y delta, delta Y, and delta delta. Now these are the three transformers. They have been connected in Y to Y, but all these four types can be connected. In the book, two more things that you have to note, that whenever it is written high, H1, H2, H3, H1, H2, H3, that means the high voltage side, and X1, X2, X3 is the low voltage side. Also, capital A, B, C is for the high voltage side. So this is for the high voltage side. And small letter A, B, C is for the low voltage side. Figure 3.17 in the book explains the single line diagram. It is shown like this. And then per unit diagram is shown here. This is for YY and Y delta I'm showing. In the book here is also given for delta delta. Now this is the diagram. This can be further simplified if we remove this, what is known as the exciting current effect. So the exciting current passes through this. If we neglect that, then our circuit will be further simplified. This is for YY and this is for Y delta. Now, a point to note is that there is a phase shift here. Plus 30 degree on the high side and 1 on the other side, or 0 on the other side. And this is for Y delta. Now in our case, we have this diagram, and low voltage side is on the left and high voltage is on the right. Now here it is high voltage on the left and low voltage on the right. Same here. So we have to just reverse this diagram. So low voltage comes on the left side and high on the right. And similarly, the other one also. The only change here will now be that the phase shift will be on the right. An important point that you have to keep in mind that when we are talking of the step-up transformer, like here, low voltage to high voltage, then the high voltage side will lead the low voltage by 30 degrees. Just shown here, it is leading by 30 degrees. Now this is the question given. It has 4 parts. I will explain each part as we go on. You can pause the video and read this. Okay, so the first, it is saying that the voltage calculation, balance YY, delta Y transformer, 3 single phase 2 winding transformers, 3 transformers, each rated as 400 MVA, so shown here 400 MVA, 13.8, 199.2 kV, so 13.8 kV on the low side and 199.2 kV on the high voltage side. Then there is a leakage reactance that we'll see in the diagram. Winding resistance and exciting currents are negligible. The high voltage windings are connected in Y. So high voltage side of this side is connected as Y. A 3-phase load. This is the load. Under balanced positive sequence conditions on the high voltage side absorb 1000 MVA. So the load power for all 3 is 1000 MVA and the power factor is 0.9 lagging. Also VAN, this VAN we already know is 199.2 kV. So it is 199.2 kV and the phase angle is taken as 0 because this is the reference phase angle. And then the question says that you have to determine VAN at the low bars if the low voltage windings are in Y or in delta. So let me explain this a little bit further. In the first case, we have low voltage Y and high voltage Y, both YY, and then the load is connected. In the second case, the low voltage is delta and high voltage is Y and the load is connected. So we have to deal them separately. Then revision of the per unit quantity. We know per unit quantity is actual quantity divided by the base value. Usually the base voltage V, base line to neutral and base complex power of single phase are selected for either single phase circuit or one phase of the 3-phase circuit. So if it is 3 transformers making a bank, then also we preferably select the single phase. So the base current will be the single phase power divided by single phase voltage, line to neutral voltage. But we can also use the 3-phase power and 3-phase voltage. With that we have to add under root 3 because this is line to line voltage. But I'll prefer and use this one. So the first part, both Y and the load. What we'll do, we'll just select one phase. So this will be our circuit, PU circuit. And in the book, he has used this circuit. So this was the part, the 0.10 is the impedance. And then we connect the load and we connect the source VAN. So this is our YY configuration. Now to apply KVL, we need to find the value of the current here. It could be IAPU current or the actual current, actual value of the current. We are calling it I high actual. And to find the PU current, load PU, remember the current through this load, we need to have the actual value divided by the base value, IH actual divided by I base high. Now, how much is I base high? We have to then find out the I from the power divided by line. So, power is up to this point, the power is 400 MVA. From here you can see 400 MVA, and the line voltage is 199.2. So, high side. And so this will be our base current, 2.0008 kiloampere. We could have used three-phase, we'll get the same result. So we have found the base. We need to find IA. Moreover, the reference, we just noting down this was the reference voltage for single line diagram or per unit diagram. It is 1 and angle 0 is taken as the reference. This we taking as reference. And then IA load PU, IH actual and I base. I base we have found already. Now IH actual we have to find. And IH actual we can find the current through this load. So we know the load power, and we will use the high side load to neutral value. Or we can use the total load power for three phase and then under root 3 VLL. Using this formula, load power for single phase will be 1000 MVA divided by 3. This is the total power divided into 3 loads. So divided by 3, and VI line to neutral is 199.2 kV. And from the power factor lagging, we can find the cosine inverse 0.9 to be the angle. And this, when we solve, we get this result. And now that we have found the IH actual, we have found the IH base. Therefore, IA load PU is this divided by the base. And this is the answer. So we just note down here that our IAPU is 0.88 with this angle. Okay, now we have to find the voltage. We have found this current, so we have to find the voltage here. So we can use the KVL equation. That this voltage is equal to VAN and the drop in X. We had already discussed that this will be 1.0 phase angle 0 as a reference. Then J and XEQ is 0.1 multiplied by IAPU, this current. Now we're removing this J by substituting plus 90. So J is removed, angle plus 90 is added. So this will be the equation, and which when we solve, we'll get this answer. Now you can use your calculator in complex mode to very easily solve this. Let me just show. So this is our calculator. It is already in complex mode, but if it is not, you can select from here mode 2 for complex. That is in complex mode. Also, this has to be in degree. And now we will add this. So 1.0. This was the mistake. So let's do it again. 1.0 plus bracket 0.0833 fifth angle 64.16, bracket close, equal sign, polar rectangular form, shift complex for polar 3, equal sign. So it is now correct 1.039 and angle is 4.13. Okay, so we have got VAN in PU. Now we have to find its actual value, VAN actual. So for actual, we have to multiply by base. And X side base is taken as the low side, this voltage 13.8. So we'll use that as base multiplied by PU. So this is our answer, 14.34, angle 4.139 kVE. So this is the first part. Now going on to the second part, our circuit will be this one. Now to connect phase by phase, we have to convert delta into Y. Converted delta into Y. And now we can take one phase from here and one phase from here and use this circuit. So this is what we will get. We connect the source and then we connect the load. And this was the phase shift from here. Now remember that the phase shift applies for the line voltage as well as the line current, same phase shift. Now we have to determine VAN here also. So first we start to find this voltage EAN. Now the ratio from here you can see is EAN over VAN is 1 divided by angle 30 or EJ30. So from here we can see that EN is VAN and this goes up, so EJ minus 30 VAN. Putting the value, this one can be written as 1 minus 30 degree angle. VAN is our reference voltage, this one, 10 and angle 0. So this is PU. EN we have found. Now we need to find IA. IA, same formula, same phase shift with the current IA here on the secondary side. This current we had already found, so we use that. The angle shift and minus this current. And now this minus 30, we can bring it here and add to the angle. So this will be per unit IA. Now VAN by the KVL is EAN and drop here. Putting in the values EAN, this value from here, and this is the value of the second part. And again, solving by using a calculator in the complex mode. This is the answer in PU. Now, what is the actual value? For that, we have to find the base. Now, there is a trick. If it was YY, then there is a direct relation between the two sides. But if it is Y delta, then we are taking the converted Y from the delta. So on the left hand side, this is the phase, and on the right hand side, this will be the phase. So VA and delta. And the relation is N1 and 2 under root 3. But in our case, it is 1, 1, because we know the angle was 1, 1 related. Just like here, it is 1 and angle 30, or 1, 1. The 1, 1 relation we'll use here. And from here, VA and delta will be VANY divided by under root 3. Now, if you are not comfortable, because you say that our delta is on the left-hand side, you just flip the circuit and you will get the same result. Okay, so we were here, VAN actual now we need. We had found out VAN PU. And so we are concentrating in this area. And we'll now use this formula from here to find VAN delta base. Per unit quantity was this one. And we need to find the base quantity to find the actual one. To find the base quantity of the low voltage side, that is the delta side, we'll use this formula. So this is the formula. Base delta will be base this divided by under root 3. And this base is on the 13.8. Here the base was 13.8 before we convert it into delta. So 13.8 divided by under root 3. So for delta, the base value will be 7.967. And now we can multiply VNPU with this. So VN actual is VNPU multiplied by the base voltage. And so the answer will be 8.278 minus 25.861 kV. So this is the answer. I hope you have been able to follow this. Please let me know through your comments. Thank you.